Okay. We'll now look at continuous one-way slabs. For example, the floor that we are sitting on, or the roof that we are sitting on. You know, there's a long corridor, a lot of bays are there. And these are column locations, you can see there. Before this false ceiling came, when did it come? 1 year back? Yeah, 1 year back. You could actually see the beams. So there are beams here, and there are slabs. This is the end. So you have what is called an exterior span, and then you have interior span. What do you think the span will be? Roughly 3 meters. 6 meters. What is the scale? 3 meters, 6 meters? Huh? You're saying one floor height is. By the way, these floor heights are also a little more than 3 meters. So it's close to 4 meters.
The span is 2.5.
Clear span.
This center to center is 2.8.
Center to center only 2.5? No. Is it 2.5?
By tiles,
By tiles, so you're a construction. By tiles, you tell me how many? Look at the tiles. 1, 2, 3, 4, 5 tiles. 10 feet. So 3 meters. Not bad. 3.25 is what something. It's not a round number. It's some point. Either. So he's saying it's 2.75. Okay, whatever. Say 3.25 meters, let's say, center to center, or 3 meter clear span, or slightly less. How will you design the slab? It's one way because in this direction is much more. Clearly one way. Tell me. At least you should know. How will you decide on the sizes? Let's say you don't worry about lateral loads, gravity loads, columns, beams, slabs. No columns are allowed inside because they'll come in the way. So let's say this is how much? 9 meters? Imagine 8 meters, 9 meters. So one way is slab. So how will you analyze it? Let's say I want to do it accurately, I want to do it crudely. Tell me both ways. Accurately?
by considering bending in both the directions.
What should I do? Don't give me theory. Yesterday we were discussing this, even if you're good in theory, in practice we are all bad. The actual construction, the roof leaks and all that. So we are all good in know-how, very bad in do-how. Now, what will you do? Let's say you got this as a job. Say manually, what will you do? Some ideas, quickly. Dead load is known, live load is known. What will be the live load for institutional buildings like this? 5 is little high, 3 is little low. Say 4 kilonewton per square meter. Okay, then what? So you know the loads. Then self-weight and take a floor finish of 1 kilonewton per meter square, right? But what to do? How to analyze? Shall we take 1 meter strip? We are allowed, no? One-way slab. We'll take a 1 meter strip. Right? How many bays should we take? Let's say there are 10 bays. We'll take all 10 bays. We'll take all 10 bays, 1 meter strip. Or we can stop somewhere. Okay, we don't know, so we'll take all 10 bays. Okay. Then what do? What support conditions shall we put? We are talking about the slab, right? So the beams are the supports for the slabs. So what will you put? Continuous slab? Is it correct? You understand what I'm saying? Shall we do this? And many people do it, by the way. Etc. etc. You can go as far as you wish, right? Then we put some loads on this. Dead load plus live load. This is okay. Is it okay or not? In what cases it's not okay? When is this truly okay? When? Now I can see his eyes is opening, as though some tube light is burning.
And alternate spans are loaded.
Arey yaar, aaram se. First, we'll talk of the loading later. First, the boundary conditions. What does this boundary condition mean? Huh? Simply support. Is it a valid boundary condition? Huh? I'm taking 1 meter strip. That means it's like a beam whose width is 1 meter. That's what we've learned. That's allowed perfectly already. 1 meter slab. I want to hear. Shall we make our life easy? We'll say there are only 3 bays, okay? Otherwise we'll get confused. We'll take only 3 bays. 3 bays. First of all, is this modeling correct or no? It assumes something. What does it assume? Huh? What does that physically mean? What are you assuming? This is valid in some cases, but perhaps not here. Perhaps it's valid.
No wall is
Huh?
no wall is
No wall? No, loads we'll see later. First, the modeling. This is predominantly a load coming from the slab itself. Okay, there's no wall. Maybe you can assume some partition wall load. We model that as a UDL. Leave that. I'm talking about this first of all, modeling as a continuous system. Is it valid or not? If we had masonry walls at all these locations, then it's valid for sure. But obviously if there's a masonry wall here, I wouldn't be able to talk to you. Right, the wall will come in the way. So we want large wall-free, column-free space. That's why we put the beam. But the beam should behave like a wall for us to model like this. So what's the requirement? The beam should be relatively rigid. Supposing I give a span to depth ratio which makes it flexible. Let's say normally we say span by 10, the depth. I do span by 20. Then it's flexible. So we are assuming the beam is rigid. But even there it's strictly not correct. So what's the correct modeling to do? The correct modeling to do, which nobody does, is to replace this with a spring. Right? Because this can handle any degree of flexibility. You understand what I'm saying? The beam is flexible. And interestingly, whatever size of beam you give, it depends on where you're cutting that 1 meter strip. If you are taking that 1 meter strip in the middle region, then the beam is more flexible there. If I'm taking at the extreme end region, it's not going to deflect much, it's more rigid there. So even the spring stiffness depends on where you're taking that 1 meter section. Agreed? How do I find out the spring stiffness? The spring is the beam. How do I find out the spring stiffness? You guys like to be spoon-fed with standard questions and answers. Real life is never standard. How do you find a spring stiffness? How do you find a spring stiffness? What is a spring constant? Force per unit deflection. Go by that definition. So what should you do? I have a beam. Let's say I'm taking the 1 meter strip in the middle. What should I do to find the spring stiffness?
Force at that section.
I apply some load P in the middle of that beam and see how much it deflects. That P by delta is a spring stiffness. Very simple. How you do it is your problem, but it can be done. You can use SAP to do it, whatever. Agreed? Let's say that beam is simply supported. Let's say it's simply supported on 2 pillars here. Then what's the spring stiffness of the beam? You guys are very good in remembering formulas, no? You reeled out that 5 by 384. What happened? Huh? So what's the stiffness of the spring? 48 EI by L cubed. But actually it's on columns. So it's going to be stiffer or less stiff? It will be stiffer. Right? So you've got some measure.
192.
192. That's when it's fixed.
Yes.
It's not fully fixed because it can rotate. So somewhere in between you can check out, right? Okay, after you got the spring stiffness, what will you do? And you got only your brain and your pen and your paper. No computer. One of them, all of them should work, but first your brain has to work. What will you do after you get the spring stiffnesses? Okay, I've replaced this with 4 springs. Now what do I do? Okay, first let's talk about the loading. He made a relevant statement that actually the dead loads you can assume to be uniform, but the live loads change. You have what is called pattern loading. For the worst case, you must assume live load in one span, no live load in the other span. We'll study this in detail little later. Okay. But let's take a simple case where everything is uniformly loaded. Okay. When the live load is low, less than 75% of the dead load, you can make this assumption. Now what to do? Mind you, when you did the continuous beam with the rigid supports, you are assuming the spring stiffness is infinite, that's all. Here you are doing it more accurate. What to do? Which method will you apply? How will you solve this problem? Spring stiffness you know, spans you know, moment distribution method. No. Any method. First of all, can we take advantage of symmetry? Can we take advantage of symmetry? If the loading is, so why we'll do that? We'll take advantage of symmetry. Half the job is simplified. And cut it here. What's the boundary condition I should put here? Huh? I'm sorry we've gone off the topic, but it's, you should know all this. What should you do? Fixed. My God. Who's fixing it? I fix it. Draw the deflected shape, yeah, it's going to deflect like this, no? And this line of symmetry, what's the one thing you're sure of at the line of axis of symmetry? Slope is 0. That means fixed end, huh? No.
Rotation restricted.
So that's called a guided fixed support, okay? So there's no shear transfer, but the slope is 0. Now you'll get more scared. As it is, spring scares you. Now this support scares you more, but you should know how to do this. Okay, give me any one method to solve these problems. By the way, this is your homework. You should know how to do all this. Or this Friday I have to go somewhere. You do this as your tutorial. We'll give you a tutorial. And to make it simple, we'll remove the spring. You can assume to. You must know how to do this hall. Your problem is this building. Just give me detailing for 2 spans, exterior span and 1 interior span. Will you do that? How to do design of slabs. Okay. Forget the beam, just the slab. Okay, tell me. So this Friday, you have to submit in class. No take home. 1 hour. Let's make your life simpler. Supposing it was not spring but the original support, how will you do it? Can you do moment distribution method? Yes. Right? What are the other methods you know? There are 2 broad categories of methods. What are they called?
Force method.
Force method and stiff and displacement method. Moment distribution method is force method or displacement method? Sure. What's the difference between force method and displacement method?
Written in force method, the forces.
So the unknowns in force method are forces and the unknowns in displacement method are displacements. One. Fantastic. In moment distribution method you find the rotations and deflections. You find only the moments, no? So is it a force method or a displacement method? Now it's become a force method.
Finds a displacement, but we do not calculate them as a value.
Do you agree with him? Is it force method or displacement method? But your fundamental definition was the unknowns are forces, the unknowns are displacement. So I am deliberately provoking you to show you that you don't know, or your knowing is a little blurred. Please read up all this. But once you've got springs, what will you do? Okay, so give me examples of displacement methods. You're right. Slope deflection method, moment distribution method, Carney's method, stiffness method, they belong to displacement method. What's the kind of indeterminacy we look at these methods? It's called kinematic indeterminacy. In force methods, static indeterminacy. What are the methods you know? Castigliano's method. Castigliano's got a theorem with 2 parts in it, but the method, I think you should read. My strong suggestion, read my own book on structural analysis. I've got 5 parts to it. Part 4 is force methods. Part 5 is displacement methods. So the easiest method to begin with is called the method of consistent deformation. Very easy. Then you have theorem of least work, also known as energy method. Then you have flexibility method, you have also column analogy method, etc. Which method will you use here? Which is the easiest method to use? Huh? You have to do it manually, boss. Manually. I told you 3 things you have: brain, pen and paper. Without computer you cannot analyze these slabs. They have been built from time immemorial when no computers were there. Razwan, you wanted to be in the best place in the world, the best institute.
Yeah.
That's not what you should want to be. You should want to be the best yourself. What's the use of being the worst in the best? So go by yourself. I want you all to be strong and confident and know that any problem can be solved. All you need is clear fundamentals. I'll give you a clue. How about energy method? Theorem of least work. So it's a force method. How many redundants you have? How many redundants you have? To make it statically determinate, what should you get rid of? Redundant means what? What does redundant mean? Redundant means what?
Extra.
Extra. Very good. Extra. Not needed to survive. Not needed for minimum stability. Right? So, what will you get rid of? You'll get rid of the thing that you don't like to see. That's the yellow line, right? So, what are the reactions you get there? You treat that as redundant. What's the reaction there? It's a moment, right? Is it a sagging moment or a hogging moment? Sagging moment, correct. So, this is your redundant. Any other redundant? Is there a vertical reaction there? No way. Right? So we will call this redundant X. Right? And these springs have a stiffness K. Both are K. The span is L. This is L by 2. This load is W. Right? How to find X?
Take moments.
How to find X? Energy method. What is the theorem of least work? Someone speak a clear sentence. What is the theorem of least work? Am I speaking Greek or? You don't know all this? You have to do this today, at home. Draw the bending moment diagram and tell me.
Sir, I'll find the strain energy.
Slow, now you're talking. In structures department you find the strain. Okay, find the strain energy. How do I find the strain energy?
Integration of m square dx by dt.
That strain energy is half integral.
M square dx by
Now the memory cells are flashing. M squared
dx
dx by
plus dt.
pi plus
Plus all other shear deformation.
that you ignore. That's all. First of all, is this the way you've written? Is it called strain energy? So even there, the fundas are weak. It's complementary strain energy. When you write in terms of forces, it's complementary strain energy. Otherwise, you should write in terms of displacement, right? But there's something you're missing, which is why I said strain energy. What is missing here?
Springs.
The springs. Springs have some. So, what's the strain energy in the spring?
Half k square.
Half K.
So delta square.
This X in this K, whatever force in the spring, right? KFS. So you have two springs. So let's say the reaction here is R1. The reaction here is R2. So you can write K into
R square by k.
no, this is wrongly written. What should I write? K.
R square by k.
So for a spring, it's half. Should be the other way, no? K will come in the denominator. R1 squared plus R2 squared. Agreed? Yes or no? At least you should. Now, this M, which is a function of X, and this R1 and this R2 can be all written as functions of X. Yes or no? So this whole thing is a function of a single unknown X. Once we find X, we can crack the problem. Right? From equilibrium, you can write a R1 and R2 in terms of X. What's the governing equation? Huh?
You del M equal to
Why do you want to bring del into the picture? There's only single unknown. So, du, by the way, u is equal to u star you can write because it's linear elastic. Okay, but this expression you said. Du is equal to, so du by dx equal to 0. It's actually a compatibility condition. You can solve. So this is the easiest method you could use, perhaps. So remember all this. It's an unusual problem. You could get it, but learn how to. Then you draw the bending moment diagram, right? Then you'll have to probably do pattern loading, change the boundary conditions, and so on. So please note, this again is tricky because there's one extreme case where your k is lowest, there your k is high. So you'll find that if you do it in using a software, you'll get fairly good results. You'll get the whole moment field with the actual modeling. The other assumption you're making is you're assuming that the beam and the slab actually you get some torsional restraint, right? Which you're ignoring. Do you know that? It's an L beam, no? So you've got a partial rotational restraint, but there's a reason why we're ignoring. We'll see that later. Is it clear? But no harm in doing this and knowing that you're making an assumption and going ahead with it. Right. So let's say you got the bending moment diagram. So the code makes your job very easy. What does the code do? The code gives you coefficients. So in wall supported and beam supported slab systems, the slab panels are generally continuous over several supporting walls or beams. One-way continuous slabs, the bending is predominantly along one direction. The arrangement of live loads. Okay, the code gives you ways of arranging the live load. Alternate spans, you put live load. Two adjacent spans, you put live loads. We'll see that later. For continuous beams or continuous secondary beams of continuous one-way slabs supported on walls or rigid beams and uniformly loaded, at least three continuous spans which do not differ by more than 15% of the longest can be used. If this condition is satisfied, then moment coefficients are given in the code which give you results that are close to the exact values obtained from rigorous analysis. We'll see this later. So the code gives you don't need to do any analysis, provided you have rigid supports and the spans are more or less equal. The code says, okay, before the code says anything, in which will I get the maximum steel requirement? In the exterior panel or the interior panel? In the exterior or the interior? Simple question. Huh? Why? In which will I need more positive steel? Sagging moment. Interior or exterior?
extreme.
You have to have clarity. You will find that always the exterior is the most critical. The bending moment here will be more than the bending moment here. So it's W U dead load into L squared by 12 plus W live load into L squared by 12. This is called the end span. The interior span is WL squared by 16 plus WL squared by 12. In the internal, the negative moment at the first interior support is WL squared by 10 plus WL squared by 9 for live load, and it's less. These are values given in the code. And the code says even though you assume this to be simply supported, you have to design for some minimum negative moment because of partial fixity. Okay, there could be a wall on top. If you have a beam, you have support. So anyway, you're going to bend up half the bars, so that will be taken care of. You should know this. Okay. There are shear coefficients also, but you don't have to worry for slabs because in slab shear stresses are negligible. So first, you should know the definition of effective span. Please go through this. We've covered it briefly. It also depends on the width of the support. If you have a very wide support, then you shouldn't worry about it. You should take clear span plus half. Now let's look at this problem. Okay, this with real dimension. So I want some of you to measure this And it's the same hall, only thing it'll be the room where you're sitting in. So the spans, will you help them with that? You work out this. But we don't put walls here, we put beams everywhere. Clear? Okay, so you got a floor slab system covering an area of 8 meter by 14.5 meter, 14.5 by 8. So it's like this hall is 14.5 meter long, 8 meter wide. And it'll be interesting to, actually what we'll do is, we will give everybody a chance to be original and not copy. So we will keep changing the span depending on your roll number. And it's interesting, but total length is same. Total hall size is same, but some people have beams at smaller intervals. Some people have it at further intervals. Is it clear? We'll do that. The slab rests on a 230 mm thick masonry wall all around. In this example, for economy, the span of the slab is reduced by providing 3 intermediate beams. The specified floor loading consists of live load of 4 kN per square meter and a dead load due to finished partitions of 1.5 in addition to self weight. Assuming, in your case, you'll assume Fe 500 grade steel and M30 grade concrete. Okay, this is Chennai. We don't want it's moderate to severe exposure. Start getting used to the idea of M25 or M30 grade concrete. Right, so you've got these dimensions, then assume each beam to be 300 mm wide, work out the spans, and then you can start, you have to work out the thickness. Now, again, the most critical panel is the exterior panel. Why? Because for the interior panel, this one way, this strip you can say is continuous here and here. But this is continuous here, but simply supported here. Remember, the thickness of the slab is governed by L by D ratios. So its L by D ratio is 20 for a simply supported case and 26 for a continuous case. For the end span, it's an average of that. Then assume a KT of 1.25, you got around 29, and so you get a minimum of 121. You add something for effective cover, round it off, make it 150, and then again say effective depth is 125. Work out the effective length more accurately. Now for the interior span it's this, for the end span it's this. For the end span it's slightly more than the interior span. You have to do this accurately. You do this only in your calculations. Don't go ahead and change the actual span at site, because it's nice to have all the spans. The clear span look the same. Work out the loads, the additional dead load. Okay, so yeah, go ahead, ask.
Sir, even in one-way slabs, won't the slab bend near the supports in the other's direction too?
Even in one-way slabs,
When the slab bends in the second way, that is the other way,
yes,
near the supports,
yes,
are we not designing for it?
we are designing for it. How those bend in one-way slabs? What's the definition of one-way slab?
It predominantly bends in one direction,
One
but
direction.
near the supports there will be a...
Near the supports. So you'll find that the deflected shape, typically you should visualize the deflection contours, but near the supports, in the other direction, even near the supports, because your moment at the support is 0, if it's simply supported, why are you worried? You understand what I'm saying? At the support, your moment is 0. You have to look at it this way. It is deflecting because predominantly of one-way action. If that edge was not there, it will still bend one way. But you got a little bending moment in the other direction, but because you're close to a simply supported edge, the actual bending moments will be very, very small. So you can work out the actual values, you will find them negligibly small under uniformly distributed load. But that's why we put distributor bars, they can easily handle that load. Again, it's sensitive to know. Let me ask you another question. Truly cylindrical bending behavior, when will you get?
Only when it is supported.
Truly cylindrical bending. Let's say I support only on two edges. Will it bend in this direction?
When the beam deflects response.
No, let's make it simple. Two walls, slab on top. Okay? If there's a slab on top, and I put uniformly distributed load, will it bend perfectly in one direction like a cylinder? Will there be bending in the other direction?
Yes.
Yes or no?
Yes.
Why?
Poison.
Why yes, why no?
Poison.
Don't bring poison into this. Okay, what is this? What are you saying? You speak clearly. We are asking a very interesting question thanks to the power cut. I want perfect bending in this direction. That means this should be straight line, no curvature. Clear? Listen to me carefully. Let's throw away supports. Manually, I put some moments here. Okay? On this edge and this edge, sagging moments. Will it bend like that? Let's say the moment I apply is m, small m, per unit length. Right? Will it bend like that? No. Why not? Because if I apply a moment only on these two edges like this, it's going to bend theoretically like that. I can find the curvature. How do I get the curvature? For beams we talk of m by EI. But for slabs you have something called D with Poisson's ratio in it. Whatever it is, I get some curvature this way. That means the top layers are subjected to compression and the bottom layers are subjected to tension. So when the top layers are subject to a compressive strain, what happens in the other direction? You will get a tensile strain which is mu times the compressive strain. Similarly, the tension here will call for a compression there. So what will happen? When I actually apply moments like this, it's not only going to do this, it's going to automatically do this. I'll get a saddle shape. Very important fundamental. Yes or no? If I want it perfectly horizontal, what should I do? I should not only do this, I should also do this. This? No. Because it's doing like that. It's hogging. So I should also, it's hogging, so I want to flatten it, so I should do this. And to do this, what's the moment I need to apply?
The hogging moment at the ends.
Not. There is a hogging curvature here, I want to get rid of it, so I have to do a sagging. But what's the sagging moment I need to apply there to make it perfectly cylindrical? I have to apply mu times the moment I apply this way, because the curvature is mu. Very interesting. Please read Timoshenko Plates and Shells. It's there in you're doing a course now, no?
Syllabus.
It's there in your syllabus.
Last chapter.
Or even theory of velocity, he covers this topic very well. Okay, so let's discuss slab. What's the remaining topic? This is the last topic, is it?
Yeah. Next, shear beams.
Okay, so we'll discuss shear less, but let's discuss slabs, more of slabs. Or do you want to discuss more of analysis? Even the board you can't see, so I can't show you. So slabs is a very interesting topic, especially when you come to flat slabs, that's outside your portions. Flat slabs are now becoming quite popular because everybody wants column-free spaces. What's the difference between a flat slab and a flat plate? What's the difference between a flat plate and a flat slab? Not heard these things? A flat plate is simply resting directly on columns without any beams, without any change in thickness. A flat slab has drops. Drops, near the column. Why do you provide those drops? Because you have a sudden stress load transmission happening there, high shear is there, so you thicken it there, you avoid punching shear. And get this. Again, let me go back to a real life situation where many years back when I was in Delhi. One of the buildings we designed again in Nehru Place, flat slab structure. We were very careful, and we visited the site, it was done well. But when they reached the roof level, and we had not changed the slab thickness, we came to know that there was a punching shear failure. That had a puzzle because the grade of concrete was the same, the slab thickness was the same, the drop size was the same, so how could you get a punching shear failure in the upper floor? So we were curious. Then we got the answer when we climbed all the floors and saw what was going on. So we could see that the contractor was very careful in the first few floors, but then he started to cheat. And it became visible because the deflections in the slabs were more as you went up. You understand what I'm saying? Now, a deflection due to self-weight cannot increase with the height of floor, and there was no live load on the structure. So it could happen only because of what's the structural variable that you will say is responsible? E, modulus of velocity. If modulus of velocity is low, it's a direct reflection on the grade of concrete. And those tests were done in IIT Delhi. They took cores and they found that the grade of concrete from M30 in the ground floor became M10 in the top floor. For various reasons, we won't get into that. Now that's a challenge. You've got a punching shear failure. By the way, when you build flat slabs, you have to be extra careful in terms of removing shuttering. What's the extra care you have to do? Even while you pour the concrete. I'm glad we are touching these topics. What's the extra care you need to take? The extra care is this. In a normal slab like this one, the slabs are thin, relatively. But when you don't have beams, the slabs are thick. 1 foot thick, 300 mm, 350 mm. They're very heavy. And the dead load of the slab is much more than the live load that will come later on the slab. So when you're doing casting a slab on one floor, normally you prop up from the floor below, right? But the green concrete of this slab that you're casting is going to add a load onto the slab below, which is more than the live load that slab has been designed for. So what should you do as a precaution? There's a real problem. See, you should think of the construction. What should you do? Is the question clear? The main load is a dead load. And you have to prop. You've seen the props that you give. You prop on the hardened slab, and that also depends on how hardened it has become. Otherwise, what should you do? You have to prop that slab also below, maybe 2-3 floors below. You have to actually do calculation, otherwise you'll get creep deflections, large deflections, and even failures in some cases. The other question I want to ask you, very tricky question. It happened. How will you solve the problem? You have a punching shear failure. one of the columns. And potentially possible in other columns. What will you do? It's already punched through it. The client says, whatever you do, nobody should know about it. What will you do? This is real life situations. These things happen. Not textbook problems, real problems. What will you do? Punching shear failures. Huh? You have to do it fast.
So provide some extra homework and provide some more recording at the head of the conflict.
Anyway, think about it. We are not saying there's only one solution. There are many solutions. Think about it. These are challenging problems. We broke our head. We did huge brainstorming sessions. We had only one night to solve it. We're a small company. Only 3 engineers. That company is 500 engineers today. When it started, only 3. Full night we broke our head over it. We argued, discussed, went for dinner, and we said yes. And it was done beautifully, executed within 1 week. Nobody knew about it. Perfect solution. I'll tell you a clue. We use steel. Structural people here, we use your material. What did we do? Oh, by the way, when you practice, you cannot be like this. The company I work for, we did everything. We did steel, we did concrete, we did composite, and we were waiting to do glass. So you don't be too over specialized. You have to know a little bit about everything. And structural analysis is common for that. Okay, we have a Gyan course by Professor Mike Schleich. He's coming end of this month. He's a good friend. I don't think there's room to accommodate you, but we'll do a video recording of those lectures. He's talking of conceptual design. So first you have to understand conceptual design with a focus on lightweight structures. Okay, so it's the classes are from 4 to 7 in the evenings, but we're already house full. We've been oversubscribed, but we'll record it and we'll show it to you later. Okay. So let me finish this. So you've got dead load, live load. You can do the factoring. You've got loads kilonewton per square meter. And then you work out these moments. You remember those? You remember this? So I call this M1, M2, M3, M4 and all that. So you can work out these calculations. Very easy to do. You can use an Excel sheet and do it. Sometimes you have to take an average when you have 2 different values. Work it out. Then take the maximum moment at the first interior support. It's a negative moment. Find out the area of steel requirement. I hope you now know the simple way of doing it. You don't have to refer to any book. And you can find out for 10 mm bars, the spacing required is this. For 8 mm bars, spacing required is this. And then you can make this table. It's a clever thing to do. So look at the table. I've got an end span and I've got an interior span. I've got end support, mid span, first interior support, mid span, and general intermediate support. Find out the moment from those moment coefficients. You've got minus means hogging moment, plus, minus, okay? WL squared by whatever, 12, 10, 16, whatever number comes. Then divided by BD squared, you got something. And using BD squared, you can find PT. This you can just write an Excel equation, you will get it, tuck. Now convert the PT by multiplying by 100 BD into AST, millimeter square per meter. You've got these two. Check for AST minimum, which is 0.12% of the cross section. So you've got this. So if you get a lower value, this is overruled by this value. Got it? Then you have a choice. You can use 10 mm bars or 8 mm bars. If you use 10 mm bars for whatever area you need, this is the spacing. If you use 8 mm bars, this is the spacing. Now here's what you have to do in practice. In practice, you can't give any arbitrary spacing that you like. You would like to match the spacings between one span and the next span. Okay, and then you can play around with 8 mm bars and 10 mm bars. That's what you should do. So you've got both options here, and you should again see the code restriction on maximum spacing. Then you choose. For example, here I choose 10 mm at 220 here, and I go multiples of that. So once I've decided 220, my other half is 110. So 8 at 110, 8 at 220, and if required, I'll put extra steel on top. Is it clear? This is how it's done in practice. So do one problem and draw a nice diagram. Okay, this is a standard diagram given in SP34. Okay, here we've not bent up bars, so everything should be crystal clear. And you have to know that how much should you extend the bar. Okay, you can curtail 50% of the bars to say curtail these bars here. So normally you curtail 50 at 0.15 from the end support and 0.25 from the intermediate support, and you extend 0.3 of this span here. You can stop this halfway through, etc., etc. So go through this detailing. I would like you to draw this yourself. I drew this in MS Word in those days. Now you have a lot of support. You can do it manually. Doubly reinforced sections, you can go through it where you have to put closed stirrups. The U shape won't work here. And the design problem is to determine ASC and AC and to restrict XU to XU max. So this is how we normally do it. We keep the neutral axis at XU max. I mean, we always doubly reinforce section when you do design. It's easiest to do it for a balanced section. So it's very simple. Find out the singly reinforced balanced section capacity, and then add to it a little extra PT and PC. Is it clear? So there's a balanced singly reinforced. You know the capacity, it's MU limit, and you know the requirement for delta MU, and then you can find out the area of steel needed. So PT is PT limit plus delta PT, and you know that delta ASC, the additional tension steel you need is MU minus MU limit divided by, because the steel is going to yield. It's the lever arm is 0.87 Fy D minus D dash, so you can easily work this out. And the area of compression steel, you just have to equate the steel, the force in compression needed to balance the force in tension. And this FSC is not necessarily 0.87 Fy. It depends on D dash by D. So you have to find, if you want to do it accurately, you have to figure out what that is. Please go through the theory behind it, and you have to ensure that it is under reinforced. Okay, so please go through these examples. I'm not going to cover them. Doubly reinforced beams. This is a reading assignment, and you will have this in your exam. Similarly with flange beam. In flange beams, you have a shortcut method which is very effective. You don't have to do any design to do a preliminary design. Find out the moment you need, and the steel needed is 0.87 Fy into a lever arm. Lever arm is the lesser of these, larger of these two, 0.9 D or D minus D Fy 2. And then you can check this out. So go through this example and see how easy it is to do this. Then you have to analyze and make sure it is. So go through these problems. I'm not going to work out these. It's up to you to read all. This is a big topic. We'll take this later. How do you curtail bars? Okay, what's the base for curtailing bars? We'll stop.